Record. Okay, grade 12. So this is my first attempt at doing a video recording for all of you. As I've said in the last couple of emails, you should all be working on electrochemistry, chapter 9, working your way through it. I'm going to take us through chapter 9 bit by bit in several short videos, 15 to 20, maybe 30 minutes. I'm not sure how long it will take. And I will send you those Word files so you can follow along as you would in a lesson. This is electrochemistry. I'm going to try and share a screen here so you can see those Word files, and I'm able to hopefully write on those files as we go along. So electrochemistry, let me just find that file right here. Okay, share that. And I think you should see me pop up over here in your corner. So this is the agenda, as usual, the type of file that you see that I give you in class. We're going to go through a general intro to what electrochemistry is, where you see it, redox reactions, reduction, oxidation reactions, and go through how to balance those redox reactions, which most of you are probably figuring out as I speak, and then predict the spontaneity of redox reactions after figuring out which is the most likely redox reaction to take place in a particular scenario, given a set of information. And that will take us to the end of chapter 9. And my hope is that this is not really, what we're doing here is not really meant to completely replace. It cannot completely replace what we're doing, what we would have done in class, but it's meant to help you get as much out of this online venture where we are all on together over the next 2 months or 2.5 months before the end of the school year. Okay, so I'll do my best to pull you along with me, or to stay alongside you. Okay, so let's go into electrochemistry. If I can scroll down here, electrochemistry is all around us, and I normally start off with a couple of balancing reactions, and if you were there the very last day before the end of the school year, you would have seen this. And I'm going to go to tablet mode, so you're going to see the top of my ceiling as the audio continues, hopefully, and I continue to write. But you can see over here, yes, tablet mode, that there are 3 equations. And from grade 10, grade 11, and this here, you should all be able to balance the first 2 reactions by inspection. So I said to you, what type of reaction is the first reaction? You'd all say, well, that is the decomposition of water, and it takes energy to decompose water, and that process is called electrolysis. So we put a coefficient of 2. Oh, pardon me, I have to choose the color here. Green is what I would like. Okay, coefficient of 2 in front of the H2O, a coefficient of 2 in front of the H2, and a coefficient of 1 in front of the in front of the oxygen. And we would and then that equation would be balanced with 4 hydrogens on the left, 4 on the right, 2 oxygens on the left, 2 on the right, and it's all done. And if we were to balance the next equation, some of you would be able to do that very quickly in your heads. The lowest common denominator between 2 and 3, since we'd balance the oxygens first, would be 2 times 3 is 6. 2 times coefficient of 3 in front of the O2 is 6. And a coefficient of 2 in front of the Al2O3 would make 6 oxygens on the right-hand side, 6 oxygens on the left, and 6 oxygens on the right. And now we would balance the second element, which is aluminum. We see that there's 1 on the left, 4 on the right. We put a coefficient of 4, and now we're done. And if I said to you then, balance the next equation, which is in fact a redox equation. I'm going to make this briefer than I normally would in class, where I'd give you probably 5 minutes to try and solve it, and very few people would be able to do that. You can see that you can balance the coppers, 1 copper on the left, if you follow that cursor, and 1 copper on the right over here. Although they are not in the same form, we have copper ion, copper 2 ion on the right, and copper with a charge of 0 on the left. Nevertheless, the coppers are balanced, left side and right side, 1 and 1. And we can balance the nitrogens, 1 nitrogen from the nitrate ion on the left, 1 nitrogen from the nitrogen dioxide molecule on the right-hand side. And now 2 elements have been balanced. And then we would go to balance the oxygens left side and right side over here, 3 on the left, 2 on the right. And some would say, well, that's not such a big deal. Lowest common denominator between 3 and 2 is 6. So 3 times 2 is 6, and 2 times 3 is 6, and now the oxygens are balanced. So now we have a problem, because now we have 3 nitrogens on the right, 2 on the left, and even though the oxygens are balanced 6 and 6, and the coppers are balanced 1 and 1, the nitrogens have become unbalanced, and this looks like it is an intractable problem. However, by the end of chapter 9, and before the end of chapter 9, if you're not there yet, you will all be able to do this. Okay, so what do we do? There is some understanding here. You can see that this the state of copper is a solid on the left. The nitrate ion is an aqueous solution. The copper ion is an aqueous solution, and the nitrogen dioxide molecule is a gas. And anytime you have a reaction that occurs in aqueous solution, and you see on the very right-hand side over here, let me just write that in green again over here. This is acidic. We know several things about acidic solution. In acidic solution, you have H plus ions. Okay, so we can use hydrogens to balance hydrogens on the left and right, which at the moment doesn't make any sense. And then we have H2O present in all aqueous solutions, H2O. And you can see that we can use the oxygen from H2O to balance oxygens, left side and right side, and the hydrogens from H2O to balance any hydrogens also on the left side and right side. So right now, as it speaks, this is unbalanced because the oxygens are not balanced. The nitrogens are balanced 1 and 1, the coppers are balanced 1 and 1, and the oxygens are unbalanced 3 and 2. How do we balance the oxygens? Well, we need a third oxygen on the right. So place an H2O on the right-hand side, and now the oxygens are balanced 3 on the right side, 3 on the left side, and the nitrogens and coppers are still balanced, but now we have 2 hydrogens on the right and none on the left, so we put 2H plus on the left-hand side, and now we have balanced all elements, hydrogen, oxygen, copper, and nitrogen in acidic solution, and we are done. And if you're able to do that, you are already at the end of chapter 9. And if you can't do that yet because you've been waiting for me to post a video or a video conference, that's fine. You have several weeks to get this together. Let's move through this. So where do you see this type of reaction? Redox chemistry. Well, it's in nature, and it's in the technological world around us. We use it every day, even though we have no idea that we're using it. We use these redox reactions just by living. They're throughout our body. And many of you that take biology have heard of certain things, but may not realize that these are redox processes, oxidation reduction reactions occurring simultaneously. So perhaps the most public example or widespread example that people would understand is the idea of batteries. And I think you may understand that batteries contain chemical reactions, and that rechargeable batteries contain reversible chemical reactions. And those reactions are reduction oxidation reactions. Okay, so we see it with battery electric vehicles, which are coming to the forefront. They're in the process of replacing the internal combustion engine as a means of providing energy for locomotion to make vehicles move. And there are all kinds of battery electric vehicles. You have fuel cell electric vehicles, the hydrogen fuel cell vehicles. And you don't have to know all this detail, just have an idea of where you're seeing it. And then batteries in general are replacing, again, combustion, dirty energy technology, burning of fossil fuels, burning of coal, burning of gasoline, burning of oil. We have these larger scale energy storage technologies, basically very large batteries with a high energy density that can store enough energy to power factories or even small towns. You may have heard about Tesla doing that in Australia and some other parts of the world in the last couple of years. And then biological significance. Wherever you have these ions and electrochemical gradients, for those biology people in the class, such as this one, the FOF1 ATPase, that takes the energy in these electrochemical gradients and stores it in these energy-carrying molecules that you know about, ATP, as well as other energy-carrying molecules in the body. There is electrochemistry involved. And although you're not shown the electrochemistry in a diagram like this in a grade 12 level biology text, in a couple of years, you'll see the electron transport chain presented in a bit more detail, or perhaps you've already seen it in a diagram, something like this, where electrons are passed from one enzyme complex to another enzyme complex, and in the process, as high energy electrons are transported from complex to complex to complex to complex, they carry energy with them, and some of that energy is transferred into NADH, FADH2, and those other energy-carrying intermediates that eventually end up having their energy stored in ATP. Okay, so if you don't follow any of this or you don't understand this diagram, the basic idea is that through a series of redox reactions, energy and is transferred through electrons, which are energy-carrying vehicles, into other important energy-carrying molecules in the body, and then all over to all the biological processes that require or that can use the energy from those molecules. Okay, so let's go to the core chemistry. Okay, we're dealing with oxidation reduction, and there are 3 definitions of oxidation and 3 definitions of reduction, but really the one that is most pertinent for this chapter is the 3rd definition of oxidation and the 3rd definition of reduction. So let's go down to number 3. It's not that you don't have to know the other ones, but this is the most important one for this chapter. So in essence, oxidation is the loss of electrons. That's as simple as that. So anytime a substance loses electrons, that substance is being oxidized. And reduction is the opposite of oxidation. Reduction is the gain of electrons. So anytime any substance, whether it's an ion, whether it's a monatomic ion, a polyatomic ion, a molecule, an atom, it doesn't matter what it is. Anytime any chemical substance gains electrons, it is in the process of being reduced. And these 2 processes, oxidation and reduction, don't occur separately from each other. They always occur. It is an exchange. It is a mutual exchange. Electrons are lost from one substance, which means they must be gained by a second substance. So while one substance is being oxidized, another substance is being reduced. Whatever you do, get that straight. There are a few acronyms, common acronyms that have been around throughout the ages. Leo the lion says GER over here, or Leo GER. Loss of electrons is oxidation, gain of electrons is reduction. That's one way of remembering it. Most people these days like oil rig. Oxidation is loss of electrons, and reduction is gain of electrons. Okay, and then what I said in the bullet points just a few moments ago, that oxidation and reduction occur simultaneously in redox reactions. Electrons are lost by one substance, gained by another. Again, it's written down for you here. And then there is some terminology surrounding the different reactants involved in these redox reactions. Okay, so I'm going to go to the top again, the top of this page over here. So oxidation and reduction occurs simultaneously. Let me just write over here in green, oxidation, reduction together. Okay, I'm going to write here, hopefully that you're seeing that. Together form redox reactions. Okay, RxNS, that's reactions. That's for you, June, if you can't read my writing. Okay. Okay, so over here, within each redox reaction, there is one reactant that is called a reducing agent, and a second reactant that is called an oxidizing agent. One of these 2 reactants loses electrons, the other gains electrons, and it says that over here, the reducing agent loses electrons and causes the other reagent to be reduced. So it is itself oxidized. Okay, so it is a little bit counterintuitive, but if something is the agent of reduction, it is reducing something else. And the flip side of that is this: an oxidizing agent is a substance that gains electrons and causes another substance to be oxidized. Okay, so it gains electrons, it is itself reduced, and it causes something else to be oxidized. Okay, so that is what you're going to see in all of these reactions. So let's start looking at reactions. It says here, write the oxidation and example number 1, write the oxidation and reduction half reactions for the following redox reaction. Okay, here is the scheme that I would like you to follow. I'm just going to find my notes that I've written out ahead of time, make sure that you get everything that you need to get. Okay, so let me find that page for a moment. Okay, stop video. What did I just do? Oh, I'm still going. Okay. Resume share. I stopped the share button. Okay, here we go. So write the oxidation. So step number 1 is, well, you have to be able to do some grade 11 chemistry here. You have to be able to take a reaction and write the net ionic equation. So the overall reaction down here that you're seeing is, if I can move this up, is zinc solid reacting with hydrochloric acid to produce zinc chloride and hydrogen gas. And you should recognize that that is a single displacement reaction. You have to be able to change that into a net ionic equation. Okay, so I'm going to do that for you in a moment. So the first thing is write, okay, a net ionic equation. Okay, and once you've done that and eliminated the spectator ions in that process, then you should be able to divide that net ionic equation or unbalanced redox reaction, divide it into 2 separate half reactions. So that's step number 2 in the scheme, divide. Okay, chemical equation into 2 half reactions. Okay, one of those half reactions is an oxidation half reaction showing the loss of electrons of one reactant, and the other is a reduction half reaction showing the gain of electrons by the second reactant. And the third step in the scheme is to place electrons in each half reaction to balance each half reaction. What do I mean by balance? I mean that the left side and the right side of each individual half reaction must have the same overall charge. They don't have to be neutral on the left and the right, but they have to have the same charge left side and right side. So step number 3, place. Okay, place electrons in each half reaction, okay, to balance. Oops. To balance them. Okay, so now let's write the net ionic equation. Okay, the net ionic equation down here, let me erase that over here. Okay, the net ionic equation. Oh my goodness. Okay, so I'm glitching a little bit. I'm touching the wrong keys. Let me go down to the right page again. Okay, so the net ionic equation for this single displacement reaction is Zn solid reacts with 2H plus aqueous ions and produces Zn2 plus aqueous ion and H2 gas. That means the 2 chloride ions on the left and the 2 chloride ions on the right-hand side are spectator ions. They don't actually react. They're not part of the actual reaction. And now let me choose a different color pen. Okay, let's choose, I think this is fuchsia. We talked about fuchsia a number of weeks ago, if you remember. I asked you to spell it as a bonus question. I think this is fuchsia. Now you have to decide what it goes in the oxidation half reaction. Something from the left side of this equation and something from the right go together in one half reaction, and the other stuff from the left and the other stuff or substances from the right-hand side go together to make up the other unbalanced half reaction. So obviously zinc from the left goes together and produces this other form of zinc ion on the right-hand side. Let's call that an oxidation half reaction. You'll see why in a second. So Zn solid produces Zn2 plus aqueous ions. And that is one unbalanced half reaction. The other one is 2H plus ions aqueous. For the time being, let's include that, producing H2 gas. That is also an unbalanced half reaction. Okay, and if you were to ask me, why is this unbalanced? Well, I see one zinc on the left, one zinc on the right. Isn't that balanced? Two hydrogens on the left here, two hydrogens on the right. For the other half reaction, isn't that balanced? It is partially balanced. The number of atoms of the zinc left and right side over here on the left are balanced. The number of atoms of hydrogen left side and right side are balanced. But you must balance the total charge left side and right side. What is the charge of this zinc atom? It is 0. What is the charge of this zinc ion? It is +2. Okay, so how do we balance that? We add electrons to either the left side or the right side, whichever side has a more positive charge. And we add as many electrons as it takes to bring down the charge of that more positive side to the same charge of the other. If this is +2 on the right and the charge on the left is 0, that means we should add 2 negative charges or 2 electrons to the right-hand side. And the total charge of +2 and -2 from the ion and the 2 negatively charged electrons adds up to 0, which is the same overall charge as this one zinc atom on the left-hand side. And we'll do something similar over here for the other half reaction. We have a total charge of 2 times +1, which is +2 on the right-hand side of this reduction half reaction. There's a typo there, if you can see right here. And a charge of 0 for this H2 molecule over here. That means we add 2 E minus on the left side of this reduction half reaction. That's a typo, sorry. Reduction half reaction. And now each of these half reactions is balanced. So what does this mean? It means that zinc, Zn, solid, each atom loses 2 electrons. Okay, and in the process, we can say that it is being oxidized. And over here, for the other reduction half reaction, we say that the H plus ions are gaining electrons. So H plus gains, okay, electrons. Each positive ion gains 1 electron. Since there are 2 positive ions, a total of 2 electrons are being gained and is being, well, what is the gain of electrons? That is the definition of a reduction, is being reduced. Okay. And now let's go down and do one more. Write a pair of balanced half reactions for the following reaction. Okay, let's split this redox, unbalanced redox reaction into 2 separate half reactions and then decide which one is reduction or oxidation. So we take one thing from the left, zinc, and that pairs up with this zinc over here, and this copper will pair up with this copper over here, and that will be the other half reaction. So Zn will change into Zn2 plus. Okay, and let me scroll down a little bit. And how do we balance this? Well, we add 2 electrons on the right-hand side, and that shows that the electrons are a product. They are being released or given away by the sink, and that is oxidation. So this is an oxidation, ox, half reaction, HR for short. Okay, and we take the copper 2 plus right over here from the left-hand side of the unbalanced redox reaction, and the copper solid from the right-hand side, the product side from the unbalanced redox reaction, and that gives us Cu 2 plus changing into Cu solid, and we balance that by adding electrons to the left-hand side. So 2E minus plus 2 copper plus 1 copper 2 plus ion produces 1 copper atom. And this is the balanced reduction half reaction. Reduction half reaction. Okay. I think I'm going to stop there. That is 25 minutes. I will go on to oxidation numbers and oxidation states in another video. Okay, so I'm going to change this back to my non-tablet form. So you see me over here again, and let's find Zoom. Okay, Zoom. How do I open this up? Oh yeah, I go to this thing over here. Open Sesame. Okay, stop video, pause share, stop video.